All right, let's look at the second part of this, growth rates of different types of functions. Uh, what this says is if you have a limit of this form, where x is going to infinity and the top and bottom are also both going to infinity, you can view it as a race between the top and bottom. Now, if you think about what's going on, the top and bottom, when the top goes to infinity, it's like it's trying to make the number itself go to infinity. If the bottom goes to infinity, it's trying to make the number itself, or I should say the quotient there, is trying to make that go to 0. So you can think of this as being like a fight or a race between those two functions. And the faster function will be the one that gets its way. And you can look at certain classes of functions that grow faster than others. And here's the chart that sort of outlines that. The faster functions are at the top and the slower ones are at the bottom. So constants are slower than logarithms. This is talking about their growth rates. Every logarithm grows slower than every root function, and every root function or polynomial grows slower than an exponential. And we kind of saw that up here. This is a really big polynomial, x to the 1000, but e to the x eventually outruns it because it's an exponential. And we saw why. If you use L'Hopital's rule a bunch of times, the exponential stays the same, and the polynomial, every time you use it, gets knocked down by 1 on its degree. So eventually, you get a constant on top. Let's look at a few examples here. On this one, we've got limit is going to infinity, and on top we've got a polynomial, and on the bottom we've got an exponential. So we can look at this and say the exponential is the one that's going to win, and it's on the bottom, so it's trying to make the thing go to 0, and that's what's going to happen. And if you wanted to, you could take this one and you could use L'Hopital's rule 9 times and see that it works out. Okay, this next one over here, what you've got here is a root function on top. I guess I should actually write that. And you've got a logarithm on bottom. So between those two, the root function is the faster, so it's going to win. And that's going to make this go to infinity. Because it's on top, it's the one trying to make it go to infinity, and it wins. Okay, this next one down here, this one's not an indeterminate form, but we can still use this idea. What you've got is a constant on top. And really, the constant, unlike the others, the constant's not trying to make it go to infinity. It's just trying to, well, it's just there. It's just a constant. But the bottom is a log. And since it grows faster than the constant as x goes to infinity, the bottom is going to win, and this is going to be 0, because the bottom grows large. All right, and this last one over here, the top is an exponential, the bottom is a polynomial, and we know that exponentials always beat polynomials because they're faster than polynomials. So the top is going to win, and this is going to go to infinity. This is another one where you can use L'Hopital's rule a bunch of times. If you use L'Hopital's rule 5 times here, eventually the bottom would just be a constant, and the top would be, well, every time you go to the next, every time you use L'Hopital's rule one more time, it's still going to be an exponential, although it's going to get multiplied by 5 each time. So that's going to go to infinity. So notice all these examples are places where we had a faster class of function, or we had the numerator and denominator are from different classes. Before we look at things where they're from the same class, I want to go back up to an example we skipped earlier. This example, example 118. if we just look at this one, we can do it now using the classes of functions. What we've got is a logarithm on top, and we've got a polynomial on bottom. Now both of these are trying to go to infinity, but since this one is a logarithm and this one is a polynomial, the polynomial is going to win. It's gonna grow faster, so it's gonna win, and therefore, since it's on the bottom, that's going to make this go to 0. Now, if we wanted to, let's actually do this one using L'Hopital's rule, because I think it's worthwhile to do. If we did it using L'Hopital's rule, we've got the limit as x goes to infinity. Limit of, or the derivative of natural log x is 1 over x. Derivative of x plus 2 is just 1. And so you've got 1 over x, 1 over infinity, gives you 0. All right, let's look at the next example down here with several problems. These are things where the top and bottom function are both from the same class. Now for these, it depends on which class you're dealing with. And we've already seen some of this. For this one, we've got infinity over infinity, and both of these are polynomials. So what's this going to give us? Well, the bottom has a larger degree, so this is going to go to 0. How do we know that? Well, we talked about that earlier in the semester. If you wanted to here, though, you could use L'Hopital's rule a couple of times. What would happen is, after 2 applications, the top would be a constant, and the bottom would be, the bottom would still have a factor of x in it. And so therefore, we'd wind up with a constant over infinity, which would give us 0. Now, exponentials work a little differently. E to the 3x over e to the 2x. If you look at this, both of these go to infinity, and they're both exponential. So if you use L'Hopital's rule, the top becomes e to the 3x times 3, and the bottom becomes e to the 2x times 2. If you use L'Hopital's rule again, the top becomes 9 e to the 3x, and the bottom becomes 4 e to the 2x. And I think you can look at that and tell that, well, e to the 3x is going to grow faster, and every time we go to the next one, the bottom, or the top gets multiplied by a bigger number than the bottom. So with this is going to go to infinity. All right, this one down here, limit of 2 to the x over 3 to the x. This is going to go to 0. How do I know that? I'm just telling you the answer. How do I know that? Well, it's because you can think of this like this. Limit as x goes to infinity is 2/3 to the x. Well, if you look at what happens when you take 2/3 and start raising it to powers, as the power goes up, what you get here is going to go to 0. Because 2/3, you can almost think of this like a sequence. 2/3, then when x is 2, you get 4/9, and then 8/27. You can see that it's going to 0. So this is 0. So I guess the takeaway here is, if you're dealing with 2 functions that are both exponentials, then instead of, well, basically the faster one is going to win and push the thing either to infinity or 0, depending on whether it's on top or bottom. This last one here, this is a pair of root functions. And this one we could use L'Hopital's rule on, But I'm just going to look at the dominant terms on top and bottom. As x goes to infinity, these are the bits that are going to matter. And so we wind up with just 1. And of course, you can always check these by looking at their graphs on Desmos or something else, and see if they're going to 0 or infinity or what. So anyway, I think I'll stop this video here, and in the next section we'll talk about indeterminate products.